Dumitrescu, and the title for my lecture is on this kind of something like physical aspects of gauge theories. That's very expansive, so I'll narrow it a little bit, but it'll have something to do with physics and with gauge theory. And as Konstantin said, I'll take questions in real time, and after the talk, and please ask lots of questions. This is a mixed audience with people who have different backgrounds, so you shouldn't feel shy to ask elementary questions early on so that we can kind of see what everybody is. I don't have a particularly set list of things that I have to cover, so I can spend more time on some things than on others. All right. So maybe the variant of the title is a bit closer to reality is I'll talk about symmetries, of course. That's what we're here for. I'll say some things about normal symmetries, but of course we're interested in generalized symmetries, higher symmetries. And then we'll try to talk about gauge theories. And in particular, their phases. One of the things that symmetries are good for, not just good for, but crucial for, are understanding phases of quantum field theories, phases of matter, phases of solid state materials, and that's one of the things I want to talk about. Okay. So before I start, I will be very thin on references during the lectures, but let me mention a couple of kind of very big picture, top-down places where you can go and read, and if you have more specific questions, I'm happy to go into specific papers or reviews. One place you can start with the Simon's lectures on categorical symmetries. Volume 1 is now on the archive. And then there are two reviews, one by John McGreevy, more from a condensed matter point of view, and one by Cordova, myself, and Trilligator, and Shao. These are both from 2022. And these things will have lots of references to the original literature. Any questions? Okay. So let me start by saying a couple of very basic things about symmetries, phases, and the Landau paradigm. And one of the kind of elephants in the room that we need to dispense with quickly, especially coming out of, say, a first course on quantum field theory, is that, at least in physics, one stumbles across the word symmetries in different contexts. And in particular, I'd like to draw a distinction and carefully separate two important notions that we usually talk about. One is global symmetries, and the other one is gauge symmetries. And historically, the sloppiness between not distinguishing these two has led to a lot of confusions, and it continues to lead to confusions, even in the literature. So this is not a kind of beginner's mistake. So it's good to try to think about it a little bit. Global symmetries are the things that mathematicians call symmetries. The reason for that is that mathematicians are sensible. They only call something a symmetry if it acts on something. And so global symmetries are the things that act on things, and more precisely on physically observable things. For example, the position of a particle. Takes a particle and moves it around, rotates it around, or takes a spin and flips it around. So it acts in a non-trivial way on something that's actually measurable. These kind of symmetries, global symmetries, because they act on things, they can have non-trivial consequences. So for example, if you study the hydrogen atom in classical mechanics or in quantum mechanics, you can use the rotational symmetry of the problem to simplify your life. You can use it to solve the problem, right? You can decouple the angular part and then solve the radial problem, and that actually makes life simpler. It also means that states in the Hilbert space in quantum mechanics, or particles in quantum field theory, come in multiplets of the symmetry. So, for example, an example from nuclear physics is that the neutron and the proton are more or less in a multiplet of isospin symmetry, and there are other examples like that. So these things have consequences. And we'll get a little bit more sophisticated about what the consequences are in different settings, but the simplest one that I already said is that in quantum mechanics, the Hilbert space is in a representation of the symmetry. Which is more or less what we learned from the early days of quantum mechanics, from Wigner and Weil and these people. Now, in quantum field theory, things get a little bit more sophisticated. Because in quantum field theory, the operators of quantum mechanics acquire a space-time label, and that endows them with a notion of locality. So in QFT, the operators get promoted to something that depend on the space-time label. This is an operator or a field. And the fact that there's now a notion of space-time with a particular dimension, and the fact that you can say whether two operators are close to each other or not, is what we mean by locality. And that notion of locality, when you combine it with the elementary notions of quantum mechanics, kind of dramatically enriches the ways that symmetries can present themselves and the ways that symmetries can act. Because they can act on things that are local in different ways. For example, the most familiar kinds of symmetries act on just the local fields or the local operators themselves, but we now also know that there are symmetries that only act on extended operators. These are the so-called higher form symmetries, and I'll talk about them later today. And there are symmetries that act on kind of higher and higher codimension subspaces of space-time. And then, of course, they can mix in various ways and talk to each other. So this notion of locality is incredibly important. And of course, in order to exploit it, we also need to ensure that not just that the fields have a space-time label, but also that the interactions, or the Hamiltonian that governs their dynamics, is local. So in relativistic quantum field theory, that's something that's ensured by Lorentz invariance. It's inconsistent to have a kind of standard quantum field theory without gravity that doesn't obey the laws of locality. But even in condensed matter systems or in statistical systems, where in principle there's no reason for things to be particularly local, there are kind of interesting regimes where that nevertheless happens. And those kind of regimes are then again described by things that are more or less similar to relativistic quantum field theory. So this is a very general notion. Very good. So as I said, the simplest kind of symmetries, the ones that we sort of first learn about in quantum field theory class, are the ones that act on the local fields themselves. So for example, you can take this field, this might be a real field. You might simply multiply it by -1 and leave the space-time label alone. So this thing doesn't touch the space-time position. Things that touch the space-time positions we call space-time symmetries. And typically the things that only kind of affect the rest we call internal symmetries or flavor symmetries, depending on the context. And these things that act on local operators now have been given the name zero-form symmetries. But as I said, the more conventional term is internal or flavor or spin flip or whatever your chosen background is. Very good. Okay. Any questions about this? So let me contrast that a little bit with the other column. Gauge symmetries. Before I start bashing gauge symmetries and tell you what they're not good for, let me remind you what they're good for and why they're so important. They're important because they are essentially unavoidable technical kind of aids or constructs in building local quantum field theories that obey the rules of locality and the Lorentz invariance that I just reminded you of, together with long-range forces. If you want to describe the long-range Coulomb force of electromagnetism in a Lorentz invariant local way, then, and you want to make this totally obvious in the way you kind of build your formalism, then you will at some point be forced to introduce something that looks like a gauge field, and that gauge field will be subject to gauge symmetry, or more precisely, gauge redundancy. So they're very useful, and we will encounter them soon, and there's every reason to study them, but it's important to remember what gauge symmetries are not. Okay. So these are useful redundancies in the description of a physical system, but they do not act on physical things, physical observables. So in particular, they have none of these interesting consequences, right? Things cannot be in representations of them because they don't act on anything. And particles can't form multiplets under them, and so forth. So that's something we just have to deal with. Instead, these are exact redundancies of the description that we sort of mod out by, if you wish, at the level of the path integral or at whatever level of the description you prefer. Another thing that cannot be is approximate, right? Global symmetries, as I reminded you of briefly in the case of, say, the degeneracy between the neutron and the proton in particle physics, is good but not exact. So the symmetry that rotates the proton into the neutron, which is called isospin, is an excellent symmetry, but it's not exact. It's approximate. And that's totally fine. What that means is that the Hamiltonian is almost invariant under the symmetry, but if you act with the symmetry, you get something that's kind of small, like the remainder. These things cannot be approximate. To the extent that they're there and they're useful, they have to be exact. Now, because gauge symmetries don't act on anything, if I hand you a physical system and I ask you what is its gauge symmetry, that's a meaningless question. You cannot tell from doing any sensible computations. You can do wrong computations and get wrong answers, but more precisely, you can do different computations and get different answers. And you might all be right. In other words, different presentations of the same physical system can start with kind of taking a big system, modding out by some gauge redundancy, and you can take different initial systems, mod them out by different things, and you might end up with the same physical observables. And so that means that the same physical system might very well be described by path integrals or Hamiltonians or Lagrangians with different looking gauge groups. And that happens all the time. We'll see an example very soon in free field theory. And it's a prototypical example of duality. The notion of duality is a little bit more expansive than that, but in this context, let's say we can have different presentations of the same system, and in particular, those different presentations might have different gauges. So we don't have to go very far to see an example of this. It happens in the theory of free photons, and we'll discuss that very soon. Yes, please.
About this exactness. So if you have, because so far I've always thought like if you have some, say, topological order, and at low energy you describe it by some gauge theory, then like in my mind it was always like this is kind of an approximate description at low energy. If you have some, I don't know, toric code and you describe it by Z2 gauge theory. But now this kind of exactness, would you say that means that really the topological order has nothing to do with the gauge theory? If it's not, because it's not present in general there, right? Only as like a low energy kind of description.
No, what you say is completely right. There's a low energy approximation in which the thing looks like Z2 gauge theory. And if you just take the approximation where it's the Z2 TQFT, that's not precise. There are small corrections coming from the high energy states, and if you ask high energy questions, you'll see that. I'm not saying that the Z2 TQFT is exact. What I'm saying is that the Z2 gauge symmetry is exact. So for example, how does the toric code know that the Z2 TQFT breaks down? Roughly speaking, it happens when you get to the scale where you actually see the physical E and M excitations. And they have some finite mass, some finite gap. And once you probe that scale, you see that the thing that you thought was a topological Z2 line is actually attached to a physical charged excitation. So that's the way that the theory knows that it isn't topological. But even in that, the Z2 gauge symmetry is exact. The Z2 gauge symmetry acts on the line, and it acts on the particle, and everything is gauge invariant. So I'm not saying that the TQFT description is exact, not at all. I'm just saying that there's no sense in which the gauge symmetry acting on it is approximate. Other questions? Yeah.
So what's the difference between this gauge symmetry and the local symmetry? I mean, you mentioned the global symmetry. In my mind, I want to, well, basically I want to ask what is local symmetry? So here you talk about gauge symmetry.
Can you say what you mean by local symmetry?
Because you talk about the global symmetry, so I want to say what's the difference between local symmetry and gauge symmetry? Because in the literature, there's very confusing discussion about this terminology.
Yes. That's another source of confusion that I haven't written down, but indeed. So sometimes people refer to gauge symmetries as local symmetries, and the reason for that is that, well, we'll see this in a second, but roughly speaking, for example, here I wrote a transformation law for the field where the field gets a minus sign at every point in spacetime. You can also envision continuous versions of this, where maybe you have some phase rotation symmetry and you can pick an angle, the same angle at every point in spacetime. Gauge symmetries, do something more dramatic. They let the angle or the sign be space-time dependent. So you can choose a different symmetry transformation at every point in space-time. So for that reason, sometimes people call them local symmetries. That's even worse. So that's true, that they act differently at every point in space-time, but that doesn't distract from the fact that at the end of the day, you're still mod out by them, and they don't act on anything physical. So at some technical operational level, when you look at your Lagrangian and your fields and you do a gauge transformation, it's true that these things are local symmetries, but you should rather think of them as local redundancies. And the reason why you need to be extra careful is that in the last 10 years or so, people have started studying systems, especially in condensed matter physics, where you have local global symmetries that deserve to be in this column that act differently in different space-time slices. For example, theories of fractons are prototypical examples of that, where you might have some system that's say on a lattice.
Subsystem symmetry.
Subsystem symmetry, right. So you can act on one plane and you do one thing, and you act on the other plane and you do another thing. You might call that a local symmetry because it depends on the space-time parameter, but it's in this column. It acts and you do not mod out by it. So the key question to decide which bucket you should put your symmetry in is, do you mod out by it or not? And as a result of that, does it act on anything physical or not? That's the only criterion.
Chiral symmetry in CFT is a local global symmetry.
Yeah, you mean the space, the current algebra symmetry?
I do, or if there's a standard global symmetry, like a G global symmetry in a CFT, it gets enhanced.
That's Moody.
To Katz-Moody, which acts differently at every point in space-time.
Exactly. Yeah, no, that's totally fair. So space-time symmetries also in general act differently at different points in space-time. And Katz-Moody symmetries, which are kind of marriages of global and space-time symmetries. Yes. Thank you. That's another example. So there are tons of examples everywhere you look. But you have to remember this one criterion so that you don't get confused. So as a result of that, as a result of this diatribe, which is hopefully a useful life lesson, depending on what kind of system you study, the thing that we are physically interested in, at least many of us, regardless of whether you're a particle physicist or a string theorist or a condensed matter physicist, is systems which are described by gauge fields or have gauge fields in them. That's because those are physically interesting and important for all sorts of reasons. But the gauge symmetry is not going to help you understand these systems better. It helps you to describe them, to write them down, to write the Hamiltonian or the path integral, but it doesn't help you solve them, because once you've written the system down, the gauge symmetry doesn't do anything interesting. Instead, what helps you understand the system better are global symmetries that actually act on that system. So the thing that we would like to understand is what are the global symmetries that act on different gauge theories that we're interested in, and what can we use to extract information about the physics. And what I'm going to do is I'm going to start with some very simple kind of low-level examples, free examples, and then we'll sort of build up slowly, and we'll see how far we get. Now, one of the things I haven't mentioned yet is the problem of solvability, or strong versus weak coupling. So I'll give you some examples that are free field theories, and in that case we'll be able to kind of see everything with our bare hands. And in principle, if you want, you can compute anything you want in a free field theory. But of course, some of the most interesting physical systems are not in any sense close to a free field theory, and so you cannot calculate or you cannot use perturbation theory the way you're usually taught. And in that case, you somehow need to figure out how to say something useful about the system. Maybe if you're very powerful, you can figure out a way to put it on the computer, and the computer will spit out a few numbers. But if you want to do something kind of complementary to that, then you need to get some handle on the dynamics that allows you to say something even if you can't solve the system. Of course, there's exactly solvable systems, integrable systems, which are very interesting, but precisely the thing that makes them integrable and solvable is also the thing that makes them very different from most physical systems, so they're sort of in a box of their own. And the good thing about global symmetries is because they're so rigid and they're subject to almost no quantum corrections and renormalizations, you can kind of track them from weak coupling to strong coupling, and they're very useful tools in understanding strongly coupled theory. All right. So far I haven't said anything about phases yet and the Landau paradigm, so let me do that. Let me give you a prototypical example of how symmetries and their realization let you say something about phases, and that's, let's say, the Ising phase transition in a magnet. If you're a field theorist, that's the same as lambda phi to the 4 theory. Right, so that's the theory of a real scalar field with a Lagrangian whose potential looks like a mass term plus a quartic. And because the potential is even in phi, this system enjoys this global Z2 symmetry, which in the context of the Ising model, which is a model of magnetism, is called a spin flip symmetry. But from the point of view of the field theory, it's just some internal Z2 symmetry that flips the sign of phi. And let's, for a moment, just analyze this model classically. Essentially, that's what Landau did. I mean, Landau's theory of phase transition is very sophisticated, but it started with the observation that you get a lot of good results by just thinking more or less classically and minimizing the classical potential. And then there's an interesting discussion to be had about when that's reliable and when it isn't. So let's analyze this potential. The important thing is that we always take lambda to be positive in order to have a nice stable potential that's bounded from below and doesn't have any runoffs to infinity. But the sign of the mass can be either sign. So if you take the mass to be positive, you get a nice convex potential like that with a minimum at the origin. And you see that in this case, the minimum, shouldn't screw this up too much, the minimum of the potential is at the origin. So this vacuum expectation value means that this is the field configuration in which the energy is minimized. And the fact that the phi field vanishes in this configuration means that the vacuum respects this kind of symmetry, right? If you had applied the symmetry kind of straightforwardly, you might have concluded that all correlation functions of phi that include an odd number of phi's should vanish. That's certainly true in quantum mechanics. And in this phase of the model, that's true. So that in this phase of the model, there's a unique vacuum. And we say that the Z2 symmetry is unbroken. Another way of saying it is that it's realized in the same way that it is in quantum mechanics. In other words, the Hilbert space that you build, like quantizing the model on top of this vacuum, sits in representations of this Z2 symmetry. So you can say whether a state is Z2 even or Z2 odd. So this is the unbroken phase. In the context of the Ising model, that would be the unmagnetized phase, the kind of high temperature phase. And then you can consider the situation where the mass has the opposite sign, where the mass is negative. And when the mass is negative, well, draw it somewhere. When the mass is negative, the potential looks like this. And now, the lowest energy states are not at phi equals 0. Famously, you have two vacua, at passing -1, depending on how we normalize our fields. And these two vacua are exchanged by the Z2 symmetry but neither of them is invariant under this symmetry. And now, this is correct classically, right? So classically, you get vacua that do not by themselves respect the selection rules of the Z2. So before I go into a detour about whether that actually happens quantum mechanically or not, let me tell you what the consequences of this are. So the consequences of this are that the Z2 is no longer realized in the same way as it is in quantum mechanics. All right? In quantum mechanics, you have one Hilbert space, it's Z2 symmetric, and it sits on this vacuum. Here, you have two vacua. Each of them is not Z2 symmetric. But the Z2 is an isomorphism between them. So you get a copy of the same Hilbert space sitting here and here. The physics in each Hilbert space is the same, but it's not Z2 symmetric. So this is called the Z2 spontaneously broken phase. In the context of the Ising model, that would be the phase with spontaneous magnetization, the ferromagnetic phase. Sometimes people in particle physics also say that the symmetry is non-linearly realized. Contrast with the fact that in quantum mechanics it is linearly realized in the sense that the symmetry acts via representations on the Hilbert space. Okay, so the Hilbert space in each vacuum is not Z2 symmetric, and so that means that there are, if you look at the correlation functions of your model, they do not obey the Z2 selection rules. That's most obvious for the VEV, right? If the VEV obeyed the Z2 selection rule, it would vanish. The fact that it doesn't is the harbinger of the rest. Now, the fact that the symmetry is spontaneously broken and that the Hilbert space isn't in representation of it doesn't mean that the symmetry doesn't do anything, that it's not good for anything. It's good for a lot of things. For example, it tells you that these two Hilbert spaces are the same. But it tells you much more than that. And even in this baby example, you already see that there's something interesting that results as a consequence of the symmetry, because the existence of these two degenerate vacua implies the presence in the system of a kind of interesting, let's call it a topological defect, right? So it's a baby version of a topological defect. That defect is the domain wall that interpolates between these two vacua. So if you divide space or space-time into two halves, space, or space-time, and you divide it into two subregions. And in one subregion, you say that the vacuum is 1, and in the other subregion, you say that the vacuum is -1, far out here on each side. Then you can solve the equations of this model, even classically if you want. And you will find that there's an interesting kink that interpolates between these two vacua. All right? And this kink is not quite what you might normally think of as a topological soliton, but it kind of is in effect a topological soliton, because the topology arises by pinning the VEV in the two different vacua at infinity. So it's forced to go through 0 in between. So this is a baby example of something interesting that happens in a spontaneously broken phase as a result of the broken symmetry. And of course, there are many, many generalizations of this. We'll see some of them. All right. So this is a brief review of the Ising model. I owe you a few words about quantum corrections to this picture, but let me now say something about phases. So I've called these two pictures, the positive M picture and the negative M picture, two different phases of the model. And clearly you can see that they're qualitatively very different. And the most sharp thing that lets you distinguish them is the way that the symmetry is realized. Okay. Here Z2 is unbroken, phi is 0, Hilbert spaces in Z2 representations. Here, that's not the case. So there's a totally rigorous distinction between these two pictures. Now that distinction is not just kind of nice for distinguishing these two phases that look different with the naked eye. It also tells you something about what happens when you try to dial continuously from one phase to the other. So let's imagine that you are somebody who is capable of dialing this mass parameter, m squared, from positive to negative. So in the case of the Ising model, you do that in a lab. You have some dial, for example, it might be temperature, and then you can dial the sign of m squared. And if this is the model of the Higgs field in particle physics, then you can't do that in the lab. But the universe did that for you. For example, early in the universe, the mass was large and positive, and now it's negative. So there's lots of places where this comes into play. And then you can ask what happens in between. And classically, of course, it's easy to say what happens in between. If you take the mass to be exactly 0, then you sit at a point that looks an awful lot like this, with an unbroken Z2 symmetry, but there's a massless particle there. All right. And the occurrence of this massless particle, which is only there at the m equals to 0 point, it's not there in the positive m phase, it's not there in the negative m phase, signals a phase transition. Okay? And the point m equals 0 is a massless phi field, and that signals a phase transition. What's a phase transition? A phase transition, depending on how rigorously you want to define it, is a situation where as you dial the parameters of your model in a nice smooth fashion, like m squared, the observables of the model, like its correlation functions, or its thermal free energy, or something like that, jump discontinuously. So that's the most dramatic thing that could happen. They could jump discontinuously. A more subtle thing that can happen is that they evolve continuously, but not analytically. And that's what happens here. So the m equals 0 point, because of the occurrence of the massless particle, kind of discontinuously changes the long distance physics, because in the massive phase, everything is exponentially decaying in position space because the mass is non-zero. But at the massless point, things are decaying like power laws. So you have this kind of special point, and when it gets into the finer grainings of different kinds of phase transition, one distinguishes between first order and second order phase transitions. And second order phase transitions are precisely the ones that look like this, where a massless particle comes down. And first order phase transition, by contrast, is where there's not necessarily a massless particle, but the vacua or the observables just jump discontinuously. So we'll see examples of that in a little bit. Now, I have only analyzed this model classically, and I'll tell you in a second that once you add quantum corrections, things get much more complicated, and some of the conclusions that I presented to you do not necessarily apply. But it turns out that the things that still apply is that as long as you take the mass to be large enough and positive, you are definitively in this phase where the symmetry is unbroken. And as long as you make the mass sufficiently negative, you are definitively in this phase also, where the symmetry is spontaneously broken. And that statement, as long as the mass is large enough, is completely safe to any quantum effects, strong coupling effects, whatever. By contrast, the region around m equals 0 is very difficult to analyze, and you have to work a lot harder. And once you know these two statements about the large mass asymptotics, you can unambiguously conclude that there has to be some phase transition in between. Because there's no way to continuously patch together these two different realizations of the global symmetry. So that was, roughly speaking, the core idea of Landau's description of phase transitions. That you can simply use the realization of global symmetries to unambiguously distinguish phases, And if you find two phases that have different realizations, there has to be a phase transition in between. Even if you don't know how to describe it or compute it, if it's difficult, you can predict it nevertheless. And so he predicted some interesting phase transitions, and this is still one of the most kind of useful and general ways we have of establishing the existence of phase transitions. By the way, that argument, that Landau argument, does not tell you what the order of the phase transition is, right? Because it's really a statement about the asymptotics being different. What happens near m equals 0 is up for grabs. Any questions so far? Yeah?
This is a naive math question. Are all two phases directly connected, or sometimes you have to pass through a third phase to go between them?
Oh yeah, so that's a good question. So in this classical analysis I did for you, there are only two phases separated by this massless point. But you know, for example, I could make the potential more complicated, adding more fields or adding more powers of phi and so forth. And then there would be many different phases, and you know, you might have to cross an intermediate phase to get from one to the other. So that's true even classically. So let me say a few things about how this discussion changes once you take into account quantum corrections and interaction effects. Right? All I've done is repeat for you Landau's beautiful picture that comes from minimizing polynomial functions, which is very beautiful, and sometimes correct, but not always correct. So we have to also understand when it can break down. The first place it breaks down, and the most obvious one, if you remember a little bit about quantum mechanics, is that if you do this in quantum mechanics, where there's really only one space-time direction, which is time, there's no space, and you analyze this potential in quantum mechanics, then famously the conclusion that I wrote here is wrong. And the reason for that is that in classical physics, of course, you just minimize the energy, so you can sit here or you can sit here, and you have to choose one. But in quantum mechanics, the Hamiltonian mixes these two states because the amplitude to tunnel from one to the other is non-zero, because in quantum mechanics you can tunnel through the barrier. So there's a non-zero matrix element of the Hamiltonian connecting these two vacua, and one can describe it in a nice way using instantons. This is kind of the prototypical example when one first encounters an instanton in quantum mechanics. Incidentally, the instanton is precisely this domain wall in the one variable that you have in quantum mechanics, which is time. And when you do this, you find that you are actually back in this picture, right? Quantum effects mix these two states in such a way that the lowest energy state is precisely the Z2 symmetric state. And the Z2 anti-symmetric state has a slight positive energy. So quantum effects can ruin this picture. But then it turns out that once you go to quantum field theory and you add even more space-time dimensions, for example, now you can go to 2 dimensions and so one space and one time, or you can go to 3 dimensions and add 2 spatial dimensions. The moment you add a spatial dimension, this picture is again correct. So this is a bit of a roller coaster. So the naive classical analysis of the symmetry breaking phase is actually correct. And the reason for that is that when you're in infinite volume in quantum field theory, the tunneling rate between these two vacua goes something like e to the minus the volume of the system. So if you take the infinite volume limit, it actually goes to 0, the tunneling is suppressed, and you have to pick one of these vacua, and that leads to spontaneous symmetry breaking in quantum field theory, just like in classical physics. All right. So the one difference is that in quantum field theory, the kind of analysis of the potential that we did is only valid, so the classical physics is good when the mass is huge. And you can say, well, huge with respect to what? Huge with respect to the other parameters of the system, which is some power of lambda. So there's a power of lambda that will have units of mass squared, and the mass has to be much bigger than this power of lambda. In that case, the conclusions of classical physics are correct. But if you're near the small mass regime, the analysis might change. And so the question that Jennifer asked before is actually not a trivial question, because even in this simple model, when you go near m equals to 0, you don't know what happens. And there could be a third phase that pops out. Sometimes people call that a quantum phase, because it doesn't show up in the classical analysis. And in order to see that, you would have to do a much more sophisticated analysis of the full quantum field theory in this small m z. Now, it turns out that in the case of the Ising model, we actually know that in every single space-time dimension, 2D, 3D, 4D, there is a single second-order phase transition at m equals to 0. But that's by no means obvious. Any other questions?
What do you need to do to check whether there is something else? What is that you need to do to check whether there is something more complicated going on at n equals 0?
Well, you have to kind of solve the theory in this small m regime. And classically, that's easy to do, but in quantum field theory, that's very hard. The reason for that is that you know, m squared over some suitable power of lambda is some kind of weak coupling or strong coupling parameter. When m squared is big, you're at weak coupling. When m squared is small, you're strongly coupled. And it turns out that dimension also plays an important role. Okay. So it turns out that there's a notion of critical dimension, which Landau understood. So let's study this theory in d space-time dimensions. There's a critical dimension, which for this model is 4. And when the space-time dimension is bigger than 4, even naively when it's equal to 4, this, we'll say something about 4 in a second, then the classical analysis was reliable. And the reason for that is that in more than 4 dimensions, this theory is not renormalizable. And therefore, even though it has terrible UV behavior, it's weakly coupled and very simple in the infrared. The fact that it's weakly coupled in the infrared means that even if you compute, for example, loop corrections in the classical analysis, they will be parametrically small. And they could not qualitatively change this picture. So,
So here D is space dimension, space time dimension. I think it's space dimension.
I'm always using space-time dimension here. What was the question? Yeah. If you think of this as a classical statistical system, you can think of it as the space dimension of that classical statistical system. I'm thinking of it as the space-time dimension of a quantum field theory. These are the same, related by a Wick rotation. Yeah. So if you're a relativistic person, you would call this 3 + 1 dimensions. In D less than 4 dimensions, for example, in D equals 2 and 3, which are the most interesting, D, from the point of view of statistical mechanics, the model is strongly coupled. And the reason for that is that if you compute, you can see that kind of by doing the standard thing that you're taught to do in field theory, which is you start with a classical solution, and then you try to compute loop corrections. That procedure is only valid if the loop corrections are small. But in this case, the loop corrections are large. And that's related to the fact that the interaction terms that I wrote down, where are they? Yep. These 2 operators are relevant operators in the language of the renormalization group in 2 and 3 dimensions. So they really dramatically change the low energy behavior of the field theory. And that manifests itself in the statement that if you try to compute perturbative corrections to the classical answer, those perturbative corrections are just huge. So they kind of completely invalidate this classical or semi-classical or perturbative approach to the analysis. And that means that in these cases, you have to actually do something else. And you can do one of two things, roughly speaking. You can put the system on a computer, which is actually eminently doable for this class of systems. And then you can simulate it, and you'll conclude that it has two phases separated by a second-order transition. Or you can try to do something more sophisticated. In 2 dimensions, it turns out the model is exactly solvable. Famously, the 2-dimensional Ising model is exactly solvable. And near the critical point, it's described by free fermions. So here, this is solvable. And indeed, there's a second-order transition. In 3 dimensions, if you're working analytically, there's no way to solve this critical theory exactly. It's not integrable. But beautiful kind of 50-year history of how you can make progress on this problem by assuming something about the phase transition. See, if you have the suspicion based on all this input that I gave you that the transition is second order, that means there should be some massless particles there that you should be able to somehow describe. And starting in the 70s, people started to fantasize about what kind of assumption one should make in order to get a handle on these massless degrees of freedom. And it turns out that the correct answer is, at least in this model, that one should assume that they enjoy an enhanced symmetry, which in this case is conformal symmetry. The model we started with is not a conformal field theory. It has all sorts of dimensionful parameters and it runs along the RG. But you zoom in on the critical point of this model, which turns out to be second order, and if you assume that, and if you further assume that the symmetry at that point is enhanced to the full space-time conformal symmetry, the maximal conformal symmetry that you can have, then this model is very, very constrained. And after many, many decades of work, essentially if you systematically impose the constraints of conformal symmetry on this model, you can more or less solve it. So this is what people call the conformal bootstrap. Okay, so any more questions about this kind of big picture introduction? Okay, so what I would like to work myself towards in the next hour or so is a discussion of how this story that I told you in the context of the Ising model changes if you go from a model that's only described by a scalar field like phi to a model that has gauge fields, okay? But in order to get there, we'll have to go through a few kind of more or less immediate generalizations. And that will also allow me to introduce some concepts that will be useful later on. So, the generalization of the Z2 Ising field phi to gauge theory would be roughly speaking something like a Z2 gauge field, much like the one in the core code that we discussed before. And that's also very interesting. We'll get back to it later. But maybe the technical simplest and also the most familiar example of gauge theory is the theory of a free photon, Maxwell theory. One gauge theory. And I want to discuss that first. And in order to do that, I'm going to generalize some of the things I told you about in the context of the Ising model to continuous symmetries. And that's going to introduce things like currents and Goldstone bosons along the way, which will be useful, that we haven't seen yet. So we're going to generalize from the Ising model. it only has discrete internal symmetries, what's called the O2 model. And the generalization is very simple. You just take the real phi of the Ising model and you make it complex. I'm going to use phi bar or phi star interchangeably. And otherwise, the Lagrangian of the model is almost the same, except that you would like to preserve the phase rotation symmetry of phi. So just like in the Ising model, we preserve the Z2 spin flip symmetry. Here we would like to preserve the phase rotation symmetry of phi, and that means we're going to take the potential to be a function of only mod phi. Otherwise, we can take it to be exactly the same, exactly what we took here, just this quartic. Very good, with positive lambda, of course. Okay, so let me say a few things about the global symmetries of this model. There are space-time symmetries that will come along for the ride. I won't say too much about them except on occasion. So I'm really interested in kind of internal symmetries here. I think that generalizes the Z2 symmetry from before. The most obvious one is the one phase rotation symmetry of phi, the thing that takes phi at a space-time point and multiplies it by some phase. And as we discussed before, you have a standard internal symmetry that phase is constant everywhere in space-time. You can also check that if you try to take this phase to be x-dependent, this would not be a symmetry of this model, roughly speaking, because the kinetic terms would ruin that for you. The potential would have this symmetry, but the kinetic terms would break it. So this is the U1 phase rotation symmetry, and this is now called a zero-form symmetry. So sometimes I'll put a subscript 0. Sometimes it's called an ordinary symmetry, sometimes, anyway. Okay. Now, because this symmetry is continuous, it has a couple of features that the Z2 symmetry from before didn't have. One thing is that we have here a continuous choice of parameter which lives in U1, right? We have an angle alpha, which is the symmetry parameter. The other thing we have, famously, is because of a theorem by Noether, we have, as a consequence of this symmetry, a conserved current. There's an operator, which I'll call J mu, which is a space-time vector, and you can figure out what it is. There's an algorithm for finding it, so Noether didn't just prove that this thing exists, she also gave a constructed algorithm for finding it. And this is the current operator. And you can check that this operator is conserved using the equations of motion of this model. One very useful thing that one can do when one has a conserved current, which we'll do in a little bit, is one can look at the generating function of correlation functions of that conserved current, and that generating function, it turns out, amounts to coupling this current to a background gauge field for this symmetry. That's an important trick that's useful for studying more subtle aspects of the current and the symmetry, for example, anomalies, or symmetry-protected topological phases, or other things like that. So we'll get to that later. And we'll start simple. It turns out that this model also has an interesting Z2 symmetry, which is the a reflection automorphism of U1 that sends phi to phi bar. So that reflection enhances the U1 symmetry to O2, and that's the reason this is called the O2 model. So this Z2 symmetry is called charge conjugation. It's going to be less important than in the Ising model because it'll turn out that charge conjugation is always unbroken in every phase of the model. So the interesting symmetry to look at here is the U1. But sometimes the whole O2 is interesting. Very good. And just as a small aside, if one is interested in the space-time symmetries of this model, if I read the kinetic terms in the way that I did, where I take all three space-time derivatives to be on equal footing, that the model has relativistic symmetry, Poincare symmetry, and since that's also a continuous symmetry, there's the conserved current associated with that. And that's famously a conserved spin 2 or symmetric tensor called the stress energy tensor that you can also find using Noether's theorem. I'm not going to write it down. But this current is present in any model that has continuous space-time symmetries. Translations, rotations, boosts, whatever. Very good. So, the analysis of the phase diagram is almost immediate, so I'm not going to write down the pictures except to make a few points of difference. So this potential you see is phase rotation invariant, right? So it only depends on the modulus of phi. And as far as the modulus of phi is concerned, the analysis looks exactly like in the Ising model. The positive mass case has phi equals 0, and the negative mass case has non-zero modulus for phi. The positive mass case is entirely analogous to the Ising model. The symmetry is unbroken, there's a unique vacuum that preserves the symmetry, there's no massless particle. The M negative case, and also the M0 case, will be a little bit different. The modulus in the negative M phase, this is the potential for the modulus in the negative M phase, will get the VEV. And since this VEV is not invariant under multiplications by this phase, the U1 symmetry will be spontaneously broken, yes.
There's coffee available right now.
Yes. Whenever you get to a good moment to pause, yes.
This is a good moment to pause. Okay, so let's pause. Thanks.